In this video, I'm going to illustrate how to carry out a chi-square goodness of fit test using SPSS. Basically, this test is carried out when you have a variable that is categorical, generally nominal or ordinal in scale. The aim is to compare the proportion of observations found at each level of your variable within your sample against some hypothesized population proportions for those same levels. For example, let's say that a previous study indicates that the proportion of undergraduate college students who intend to go to graduate school after completing their degree is 0.3, meaning essentially that 30% of the students in that sample were intending to go to college. This also means that the proportion in that study who intended not to go to college is 0.7. So furthermore, let's suppose I collect data from a sample of 100 students at another university, and I want to compare the proportion of students intending versus not intending to go to graduate school for that sample against the proportions suggested by the previous study. If my sample proportions are 0.65 for yes and 0.35 for no, respectively, then I'm comparing these sample proportions against the hypothesized population proportions of 0.3 and 0.7 from the previous study. If the proportions are not significantly different, then I would infer that my sample is coming from the same population on the intend variable as that reflected in the previous study. This, in fact, is the null hypothesis. If the proportions are significantly different, then I would infer that my sample data and the sample from the previous study come from different populations on the intend variable. So the chi-square goodness of fit test is our strategy for testing whether there are significant differences in proportions between our sample data and our sample proportions and hypothesized population proportions. Also, keep in mind that when we have a categorical variable with two levels, in theory we could use something like a binomial test, but like I said, we're basically going to focus on the chi-square test in this illustration. So I have a data set, and we don't actually see the case numbers here, but this is an SPSS data file with 3 variables, and 46 individuals have responded to these measures of these 3 concepts. Intention to vote, which is coded 1 for no and 2 for yes. So basically it's a binary variable. Year in school, which is coded 1 for freshman, 2 for sophomore, 3 for junior, and 4 for senior. Party identification, which is coded 1 for Republican, 2 for Democrat, and 3 for independent. So for starters, let's say that I am a researcher and I am studying intention to vote, and let's say that I've collected data from these 46 individuals within this data set here on my intention to vote variable. Again, 1's representing no, 2's representing yes. And let's say I want to compare the proportion of yeses and nos observed in the current sample against some hypothesized population proportions. For instance, maybe these are proportions that were reported in a previous research study or some other venue. And let's say the proportions that I hypothesize are proportions of 0.4 for no and 0.6 for yes. In other words, 40% would say no and 60% would say yes. What this would mean is that if in my sample, if those proportions held, then I would expect a frequency count of 18.4 no's out of the 46 cases and 27.6 yeses out of my 46 cases. So what I'm essentially doing is testing whether the frequency counts observed in my data are different from those expected counts that would be based on the null hypothesis being true, which is that the proportions from my sample data match the proportions that are hypothesized. So we go to analyze, non-parametric tests, and then to legacy dialogues, and then to chi-square. So I'm going to move my intention to vote variable over, and where it says values, I'm going to click on this, and basically you enter in the proportions, or the hypothesized population proportions in the order of the values as they appear in your data set. So we have values of 1 and 2 in our data set. So we would enter the proportion for the no's first, given that they are coded a 1. And so the hypothesized proportion of no's is 0.40. So then I will click on add, and then I'll have to erase this, and basically I'll type in 0.6 for the 2's, which are the yeses. So at this point, what I will do is I will click on OK, and now you can see I have a chi-square goodness of fit test. So you'll see in the table that I have the observed frequencies. These are the frequency counts. For no, it was 29. For yes, it was 17. So obviously that sums to 46, which is our sample size. The expected N is, again, what we would expect if the null hypothesis was true, meaning that our sample was representing the same population as essentially the group that we're comparing against. So in terms of the expected N, we would expect if indeed our sample data was coming from a population where the proportions are 0.4 and 0.6 for yeses, for no's and yeses, then we would expect these frequency counts. So this is what we're observing, and this is what we would be expecting if the null were actually true. So the residual is basically computed as, and basically we could kind of label this columns O and this column E, and the residual is just nothing more than the difference between the two. So if we just take O minus E, our observed frequency count, minus expected frequency counts, that's what gets us our residual. So it tells us how closely our model fits, our sample data fits with the null. And so in terms of the frequency counts. So you can see that basically if we take the observed N of 29 minus 18.4, then what we observed in our data was 10.6. Basically we observed 10.6 more no's than what we would expect if the null hypothesis was true. We observed basically 10.6 less than what we would expect if the null was true within our sample data as it pertains to the yeses. So the residuals is just representing that difference between what's observed and what we would expect if the null hypothesis is true. So down here we have the chi-square test statistic, and then we have a p-value. So this is our p-value, and we would compare this p-value against some alpha level. Typically the alpha level is 0.05. So typically we would say, if the p-value is less than or equal to 0.05, then we would reject the null and conclude that our sample was coming from a different population group from that where the expected proportions are 0.4 and 0.6. So in this particular case, we do see that our p-value is equal to 0.001, and that's clearly less than an alpha level at 0.05. So we would reject the null, and we would infer that our sample proportions are indeed significantly different from hypothesized population proportions of 0.4 and 0.6 for the no's and the yeses respectively. For the next example, let's say I am testing whether there are significant differences in the proportion of Republicans, Democrats, and Independents observed in my sample data and the proportions in some null population let's say the null population proportions of Republicans, Democrats, and Independents is 0.35, 0.45, and 0.20. So let's say, where might I get those proportions? Let's say, another researcher has studied political party identification at universities and found at the university in that person's sample that the proportion of Republicans was 0.35, Democrats was 0.45, and Independents was 0.2. So let's say I want to test whether the proportions observed in my sample are significantly different from the proportions observed in that previous study. So that's where I might get those particular values. So, kind of going back and thinking about what we would expect if our sample was coming from the same population that had those proportions of 0.35, 0.45, and 0.20 respectively, we would have expected frequency counts for Republicans of 16.1. For Democrats, it would be 20.7, and for Independents, it would be 9.2. So let's run the analysis in order to test differences in the proportions. So if we go down to Legacy Dialogues, chi-square again, I'm going to reset everything. I'm going to move party over to the test variables list. So we know that the Republicans were coded 1, so we're going to give that proportion first. So the hypothesized population proportion is 0.35. I'll add there. For Democrats, it was 0.45, so I'll click there since they were group 2. And the Independents, they were group 3, and they will be coded 0.20. They'll be given a value of 0.20, and we click Add here. So then when we click on OK, you can see that we have our observed and expected frequency counts for each of the groups, and so the expected ends are exactly what we just laid out in terms of what these are. Again, what we would expect if, in terms of the frequencies, if our sample was coming from the same population as that reflected in the null population proportions. Basically, what that means is that this is what we would expect if our sample is coming from the same population as or the same university type or whatever on this particular variable as what was seen in the previous study. So at any rate, what we observed in our sample, we had a frequency count of 24 Republicans. What was expected if the null was true was 16.1, so the residual is 7.9. So in other words, we observed 7.9 cases more than what was expected if the null is actually true. For the Democrats, we observed 15. What was expected was 20.7. So we actually observed 5.7 fewer Democrats in our sample than what would be expected. And then for the Independents, we had 7 observed Independents in our sample. What was expected was 9.2. So we actually observed 2.2 fewer cases than what was expected if the null is true. So these are our residuals, which is just taking the observed frequency counts from this column and subtracting the expected frequency counts from this column. So in terms of our test statistics, again, this is our chi-square test value, and then this is the p-value, and so again we'll compare this against an alpha level of 0.05, and so we actually see that the p-value is actually equal to 0.05 in our data, which are within our sample. So assuming an alpha level of 0.05, we would reject the null and infer that the two groups are basically representing different population groups, or basically our sample is coming from a different population group from the sample that was utilized in that previous study. So the last thing that I want to show you is if we go under actually, let's go back to our data set, and we have the year variable, which again, ones are representing freshmen, twos representing sophomores, threes representing juniors, and four are representing seniors. So we'll have a little bit of a twist on this, on what we're doing, which is, let's say I want to test in my sample whether there are significant differences in the proportions of freshmen, sophomores, juniors, and seniors. I can still utilize the chi-square goodness of fit test to do this. And the way this works is that if the proportions that I observe in my sample are equal, obviously then those proportions would, the hypothesized proportions for each of those groups would be 0.25, because we have 4 groups. So the hypothesized proportions for those groups are 0.25. So really what we're doing in this particular case is comparing the sample proportions against hypothesized proportions of 0.25, 0.25, 0.25, and 0.25 for freshmen, sophomores, juniors, and seniors, respectively. So let me show you what I mean by this. If we go to Analyze, Nonparametrics, and Legacy Dialogues in chi-square again, I'm going to reset. And so in this case right here, I'm going to move the year over. And I could, in theory, lay out my hypothesized population proportions as follows. I could say 0.25, 0.25 again, 0.25, and 0.25. I could do that and basically run the chi-square test, and this is what I end up with down here. So in this particular case, essentially what this would signify is that there's no difference between the proportions that I observed in my sample data and the proportions that would be expected, or what are hypothesized under the null, which is that the proportions are equal within a null population. So you can see that the chi-square value is here, and the p-value is 0.687, which indicates that there's no significant difference. So obviously the p-value is greater than 0.05. A quicker way of doing this, a little bit less painful way of doing this, is just to click on move year over and leave it as all categories equal. So if I run that and click on OK, you can see that I end up with exactly the same values that I had above. So again, you can basically see that in terms of the freshmen, the expected ends, these are what are expected if the proportion of freshmen, sophomores, juniors, and seniors is 0.25, 0.25, and 0.25, and 0.25 respectively. So what we're doing is testing whether what we observe in our data is significantly different from what we'd expect, given a population where those proportions are in play. So you can see, again, these are our residuals, and you can see that the residuals are actually fairly small. So you can see that our observed count was just a little bit smaller than what would be expected under the null for the freshmen, juniors, and seniors, whereas it's a little bit larger for the sophomores relative to the expected. And so once again, we see that there's no significant difference between the proportions observed in our sample and the proportions in a population, essentially where the proportions are 0.25 for all 4 groups. So at any rate, this was just sort of a quick and dirty discussion of using chi-square tests with SPSS.